All right. Hopefully, I find you all happy, healthy, and maybe even starting to enjoy some sunshine. First time sun's been out around here for about a week. It's starting to shine, dry things out, and now I got to think about going and mowing. Um, anyway, today we're going to do Chapter 15, Weather and Mass Wasting. Again, this comes from the McKnight Physical Geography of Landscape Appreciation, published by Pearson. Okay. I believe I can get all this done in one video rather than breaking it down into part one, part two. So if you go on to YouTube when you're watching this and you don't see a part one, part two by it, that's because it's just one video. I only put part one or part two when it's broken down. I think I can get all this done, only time will tell. We'll see at the end of the video if it records or not. Okay? Another thing I'm going to do is for my class to make sure everybody's doing what they're supposed to do and adjusting to this whole online teaching rather than face-to-face. And for the fact that we still have some points out there that they can gain for in-class quizzes, which obviously you can't have an in-class quiz when you're not in class. I'm going to show an object from now on each of my videos, and this will go towards the online quiz or the in-class quiz. I will inform you more about that, how that works, whenever I email you with all the information about how we have turned this into an online course. But just pay attention throughout the video, and you will see a marker that you need to write down and will be asked about later. Okay, let's get going here. Weathering and mass wasting. Denudation, weathering rock openings, weathering agents, and mass wasting. Here we go. Denudation. We've heard that word before. We heard it a couple chapters ago. All right, denudation is the overall lowering of the landscape. And it's going to start out with weathering, breaking those rocks down, and then erosion, and then mass wasting. Okay? So there's three types of activity. Weathering, breaking it down. Mass wasting, the short distance downslope movement, going from the top to the bottom. Now, when we say short distance, usually rocks and stuff, they're going to get caught up on trees and stuff. So, you know, it's not, for the most part, now every once in a while you get a big rock fall, boom, from the top of the hill all the way to the bottom. But for the most part, it takes time for this stuff to work its way all the way down to the valley, and eventually into a stream or a river where it's toted away and deposited somewhere else. Erosion, removal, transportation, and deposition over a wide area. Okay? Fragmentation of the bedrock. Mass wasting can result in open scar on the landscape. All right, you can see things that have broken off and moved around. I believe this is Snake River or the Colorado River, whichever one runs through the Grand Canyon there. I forget, and I'm a geographer. Imagine that. But anyway, it runs through the Grand Canyon. Now, during times of high water, when we say sea level is high and what have you, the water is more up here at the top, and it's meandering back and forth between these hills, way up here. But during dry periods, which we are considered to be in a dry period, it finds a channel, and once it finds that channel, then it no longer moves around much. It still moves around, just not nearly as much, but instead it incisors. It begins to cut down through the landscape. You keep it in that channel, and it's just going to keep scouring, and scraping, and weathering, eroding all that material and moving it down slope and down valley, okay? Downstream. The Grand Canyon here is a perfect example. So weathering destroys bedrock and fragments it into smaller components. Now remember, bedrock, that's at our horizon, and the stuff above it's the sea horizon, right? So weathering destroys that bedrock, breaks it down. Once rock is exposed, as soon as it's exposed to the atmosphere, to the elements, it starts undergoing weathering. No matter how hard the rock is, it begins to undergo weathering at that point in time. Now, it may take a long time to weather off some of it, but nonetheless, that first raindrop, that first wind, it's starting to weather, it's starting to break down. Okay? Openings in bedrock surface allow weathering to transfer deeper. And we're going to get into ice wedging and what have you, but moisture and stuff get down in those cracks, and depending on how cold it is and how hot it is, you're going to have some contraction, expansion. It's going to open up the pores and continue to break all that material down. Okay, the openings are typically microscopic. We can see a lot of big ones, but remember, 50% of all rock is pore space. which means we don't see all those tiny, tiny little pores, right? And the water and the air get into those pores and begin to weather and erode. All right, 5 types of opening. Microscopic, numerous, occur in spaces between the rock crystals. There you go. Rock crystals are small, okay? And it gets in there and it begins to erode away. Joints, cracks resulting from stress that do not show appreciable displacement. Now, here's the difference. A joint is a broken thing, but there's no movement, okay? And we're going to show you a joint here in a minute, all right? A fault has movement. So a joint, no movement. A fault has movement, okay? Faults, breaks in the bedrock with displacement. So again, here's my handy little pin. Here is my joint. No movement. Not up, not down, not sideways. Faulting, on the other hand, right here, okay, one block moves away from the other. Now, in our last chapter, I told you there's a word I wanted you to remember, and that's this one. Lava vesicles. Gas openings in cooled lava. Again, pore space. And then we have solution cavities. Holes created by percolating water. Okay, water percolates up. We even have springs. Springs are percolating water up, right? And that water moves those sediments and stuff around. All right, the importance of jointing. Almost all lithospheric bedrock is jointed. It's got some crack someplace, right? And the rock climbers love this stuff. Rock climbers absolutely love it. So right here we go. Here's our bedding planes, which shows us our strata, our horizontal strata. Here's my vertical planes, okay? That's my joints. And the rock climbers, they really love these, the master joints. That's the ones they wedge their body into and they're trying to move up, skinny up that wall, okay? They like those master joints. The block separation is evident since weathering emphasizes fracture. And what that simply means is if water and stuff can get down, it's going to weather away more, okay? It can't weather away if the water can't get down there. But the more water gets in there, the more weathering takes place. All right, and these are joint systems. Large joints extend through a large distance and thickness are called master joints. All right, most are atmospheric, weathering agents that is. Oxygen, carbon dioxide, water is the most important. Remember, water always takes the path of least resistance, okay? Number one, we're going to get into streams in a later chapter. Number one, water always takes the path of least resistance and does, for the most part, there's only one other thing that does just as much, and that's glaciers, but water, for the most part, all right, is the largest weathering / erosion element we have, okay? Temperature changes, okay? Here we go, freeze thaw. Right? Water gets in, it freezes, it expands, okay? And it pushes those joints and stuff even wider open, maybe even breaks off some chunks. And then what happens? It melts. Now it's water, right? It moves that material, that sediment, out and down and away from that joint area, exposing more of the joint. More water gets in, it freezes, it thaws, and moves that material again away, okay? All right, which is water penetration in the bedrock openings. Biotic agents. Burrowing and or plant roots. Trees get in. They find a joint. They've got to go somewhere. Have you ever seen a tree that's like sticking out off the side of a mountain, right? Let me tell you, if it can find a place to grow, it's going to. You give it the right amount of water, something to anchor on, and a little bit of soil or nutrients that it can get, it's going to grow. Around here in Oklahoma, we got these silver maples. Oh. You know, they got the little wind peller thing, you know, little ropeller thing that the seeds are in this thing and it floats off the trees. And I've seen them grow between the bricks on my house and everything else. Those things get into a cavity and they get wet. They start to sprout and grow. I'm out there trying to pull them out of the side of the house from time to time. Just depends on how much the wind's blowing when those seeds come off the tree. It's really bad because around here you want to plant your garden. You get out there, you till and you get your garden all ready. And you're like, oh, I got my garden ready. And then along comes a storm and the wind and blows all them little wind peller things into your garden, and you got little trees growing all summer long. You're out there trying to pull little bitty trees out. So anyway, burrowing plants, animals, so on and so forth. Another one is chemical alterations. Got to remember, rocks and stuff have chemicals. They have carbon dioxide. Everything that's in the atmosphere is in that pore space, including things that make up the rocks. For instance, iron. And iron is, when it gets wet, is rust. Okay? 3 principal categories. We have mechanical, just a straight up movement of water. Chemical, like I said, you got iron, limestone, and we have the biotic, animals and plants. So let's go with mechanical weathering, physical disintegration of rocks without changes to its chemical composition. I'm not changing anything about the rock, I'm just breaking it down. Frost wedging, freeze thaw action. Here we go, perfect picture here, right? I got water in here, right? That water's going to turn around and freeze, right? It's going to expand that joint. It maybe even pushes off, and then it melts and it washes all that sediment and everything out, and then refills, refreezes, and the cycle goes again and again and again. Okay, all right. Process repeats. Frost. It's also known as frost shattering. Now, on the other side, now that's in a wet, cold environment. How about a hot, dry environment? Well, now we have salt wedging. Okay, what is salt wedging? Well, salt does the same thing. When it's arid enough, all the moisture evaporates, it leaves behind the salt. And remember, halide is a crystal. Aha! It's a mineral, right? With crystal formation, which means if it stays hot enough, dry enough, those halide or salt minerals begin to coalesce together and expanding and getting bigger and bigger. If they have a joint that they found a way into, they keep growing until they bust that joint. Thing is, salt wedging takes a lot longer than frost wedging or frost shattering. Okay, salt wedging takes a long, long time. It's not going to happen overnight. This is going to take years, but it's still an agent. All right, so salt left behind from evaporated water collects and pries apart rock openings. Temperature changes, diurnal and seasonal temperature fluctuations modify volume slightly. Depends on where you're at, how cold it is, so on and so forth. Fracturing rock over long time scales. Again, especially in the salt wedging, it's going to take a long time. It's not happening overnight. Now, if you watch it for a while, it could, right? You might see it, but it takes a while. All right, exfoliation. This is like dome rock out in Yosemite. Curved layers peel off the bedrock. Exfoliation dome. So what happens is you've got this bedrock, but it's in layers, stratified layers, and the moisture stuff gets between the stratification. And so when it does, when a piece breaks off, the whole thing slides off like an onion peel. Okay, it's just like doing an onion. You're slicing it, and that whole section, or like a tree ring, that whole section is going to come off. Okay, and it's unloading through erosion and hydration. Hydration means water. Okay, other mechanical processes, chemical and biotic impacts on mechanical weathering. Again, if you got mechanical weathering, water. Most things need water, trees, animals, so on and so forth. They're going to go where the water's at. How about some chemical weathering? Decomposition of rock material through chemical alteration of the minerals, right? We're talking limestone here. Limestone, you erode it out to make caves. We got that in another chapter. But then you end up with stalactites, stalagmites. Here we have some rust going on. Okay, here's my rust I'm talking about. This rock has a lot of iron in it. So I got this rust-colored bands here, right? It exposed to, the water is exposed to a greater surface area. So this is more like what we call a surface wash, where the water's not in a stream. It's just coming over the side of a mountain, okay? So it's not channeled, right? Oxidation, oxygen combined with metallic elements or minerals to form new products. Usually oxidation causes things to be softer, right? And here we go, iron oxide for rusting. Hydrolysis is a weathering agent, union of water and other substances, to produce a new substance. Okay, limestone is one. Igneous rock is partially susceptible. Okay, carbonation, reaction between carbon dioxide and carbonate rocks. So these are all different types of weathering agents. It's just a matter of what is affected by what. Less common processes exist as well, and chemically weathered rocks are less coherent and have loose particles, okay, because it's breaking that sediment down. Biological weathering. Plants and animals alter the rock structure, right? There we got some, I call them lichens. I'm not going to pronounce it right ever. But anyway, they're on these rocks. Again, it's like a moss, and it takes a long time. Is it changing the rock? Is it breaking it down? Yeah, but it's not going to do it overnight. Okay, that's something you're going to, well, let's put it this way, you won't live long enough to see it. And then we got burrowing animals. Remember our prairie dogs earlier? They're tearing everything up. All right, so you've got burrowing animals and everything else moving things around and changing things. All right. Climate and weathering. High temperature and abundant precipitation increase the chemical weathering. Remember, I told you back out in western Oklahoma, what was you going to find when you're digging in the dirt? Calcium carbonate nodules. Comes off the plant roots, right? You get this calcium carbonate, and it's little bitty, what do I want to call it, little minerals, okay, little specks, and then they begin to coalesce together, and they get bigger and bigger and bigger until they turn into caliche, which is hard rock, okay? Differential weathering. Rocks weather differentially. You need to know this. Remember, water takes the path of least resistance, and the thing that's going to get eroded is the softer stuff first. The harder stuff will be left behind. The softer stuff gets eroded. So rocks weather differentially. You have a hard layer up top, a softer layer. You're going to see that softer layer erode away, okay? And then the big rock on top is going to fall over. And it's not because it fell over because of mass wasting, or it is mass wasting, but not because it eroded, but because all the softer stuff eroded, okay? So rocks weather differentially. It's just like water taking the path of least resistance. All right, so mass wasting, a process by which weathered material is moved short distances by gravity. Now, factors that influence mass wasting. It's not just that simple. There's a lot of things that go into it. Angle of repose. What is the angle of repose? Well, that is the angle that it takes for something to move by gravity down a slope or down angle. It's usually between 32 and 34 degrees, so roughly 33. That's the average. Okay, so what does that mean? Well, let's draw me a little sand dune here, and sand is right at 33. Okay, so I got a little sand dune here, and I'm dropping my sand pieces all over the place here. Okay, hopefully you see these little dots, but I'm building this up, right? And I get my sand dune built straight up to like 33 degrees. Okay, because until it hits that angle, they're just going to keep stacking up in place. But once they've stacked up and I've gotten it at 33 degrees, the next part I drop is going to go down the hill, because that's the angle of repose, 33 degrees. It says when you drop something, if the angle is 33 degrees, it should bounce down the hill. Okay, now some other things though that go into play. That's sand. Okay, sand dunes, that's pretty simple. The impact of water on lubrication of rock material. Okay, what kind of soil is it? What kind, I mean, do I have a round rock, kind of like a sand pebble or sand grain, or do I have a big square boulder? I mean, could you imagine pushing a boulder down a Cimarron River? Your angle of repose is going to have to be a lot more than 33 degrees. Okay, but here we go. So, is it a square boulder? Are you trying to roll it down a hill with grass? Are you trying to roll it down a pile of rocks that are all built up with rocks? Or are you trying to push this down soft, muddy, mushy dirt where it's just going to sink in when it falls? So there's a lot of other elements at play here, okay? Some of them, impact of water on lubrication. Is it slick? Clay, water mixture, very slick and mobile substances. Maybe it hits, it slides, okay? Quick clays, absorb water, they're slick, okay? But again, how much water is there? How mushy are there? Because it's got to be just right. That rock, and it depends on the size of the rock, right? Is it a little rock? Is it a big rock? Big rock, you drop it, it's just going to sink, right? I'm going to have to wait for the water to erode all the dirt out from under it before it can fall. And even then, if there's that much water to do that much erosion, it's probably just going to fall a little bit and sink again, okay? So it depends on how much water and everything. Subarctic mass wasting, permafrost. Permafrost used to be right up to the top layer, right? Right at the topsoil, right? And over the years of global warming, it's starting to go deeper and deeper. The active layer is what we call it. The active layer is getting deeper to where they can start growing some root vegetables and stuff now on the top during the spring and summertime, right? Before it refreezes in the winter, but they can grow some vegetables and stuff. The thing is, buildings and stuff that were built when that ground was originally frozen solid and people really couldn't dig in it, those buildings are starting to shift and sink, okay, because they're readjusting to that new active layer, which is now deeper in the soil, okay? All right, so here's a great figure. I love this. Types of mass wasting. All right, here we have our moisture, anywhere from wet to dry, okay, wet to dry right there, and speed, whether it moves fast or slow, okay? So anyway, if you have something that is dry and fast, the fastest, driest thing is what we call a rock fall right there. Boom, rock fall. Drop a rock. That's it, right? You're on the side of a cliff, right? Get a little bit of heat, whatever, maybe a tree roots pushed it right up to the edge, and then a little bitty gust of wind comes along, rock fall. Okay, a landslide. There you need a little more water, right? Here's my moisture. My moisture level's going up. All right, so I got a landslide. All right, add a little bit of moisture, the whole side of the mountain comes off, right? And then we got mud flow. Mud flow is a little bit different because it's usually associated with arid lands that get those thunder boomer type rainfalls, right? So you have wind etching away and it's building up all this dust, building it up in these canyons. And then you get a thunder boomer rainstorm that comes along, basically a flash flood, and it picks up all that loose dust and flushes it right out of the canyon. Okay, that's a mud flow. Earth flow and slump, pretty much the same thing. Okay, earth flow, you got water. Maybe there was, something, again, maybe the sediments weren't the same, so you got dirt, and then there was a hole there at once, and that hole filled in with some other stuff, and so it's not constituted the same. Okay, the makeup is different, and that water gets in there, and you got too much, and it just washes that stuff out because it's a different material. Same thing with slump. It's this where, these fragmented sections kind of break off. All right, again, usually more water. So you can see more water, a little less water with the slump, but the speed is slowing down. These are also slower actions, okay? The slowest action we see here in Oklahoma and North America in general, well, actually most places, is creep, okay? It's creep. And you're driving down a road and you see, the electric poles, telephone poles, electric poles, whatever you want to call them, and are stacked up straight in line. And then all of a sudden it looks like some drunk guy started putting them in, right? And you're like, what happened? That's creep, right? It means that maybe the overall slope of the land, there's not a whole lot of slope there, but what there is, that water when it rains, it's just moving at a little time. And you're talking maybe centimeters over multiple years, right? So you can see fences, all kinds of stuff that kind of get out. Now, you got to be careful though. What's the difference between creep and our faulting or folding earlier? Remember, we said the same thing. Sometimes that line looks like, yeah. Well, it depends. There's different actions. So just because you see a fence line that's curved and looks like somebody was drunk out there doing it, no. Could be creep, could be faulting, could be a lot of things, okay? So anyway, just be wary. There's different things going on at play there. Solar fluxion, the slowest. Now, creep here is the slowest that we see in Oklahoma, okay? The only thing that is slower than creep is solar fluxion, and it takes place in the northern latitudes, okay? This happens when the ice freezes and thaws. It moves things just a little bit. It freezes, it thaws. It freezes, it thaws, okay? So it moves really slowly through a freeze-thaw cycle. Now, if you ever get a chance, look up Death Valley's Rock Raceway. Google it if you get a chance. It's awesome. You're not supposed to move things in Death Valley, and so scientists, they go out there and they're looking at the whole salt wedging and everything else, right? And they notice rocks are being moved around it. And you can see these trails, though, and it's like, wait a minute, is somebody out here messing with us? Messing with the research, picking things up? What are they doing? So it took them a while to figure it out, so they set up some cameras. And what they found out is it gets cold enough in Death Valley at night, a thin film of ice or frost would build up, just enough to lift the rock up. And then as soon as the sun came out, it'd melt, and the rock would slide down. And so the rock is actually leaving a path all the way around, kind of snake-like. So it's really cool. So look it up, Raceway, Death Valley. It's really cool. They got some videos and stuff. It's awesome. Okay, science. I love science. All right, so here we go through all of our mass wastings. First of all, rock fall. Boom, rock goes down. Okay, here's a mountain, right? And here is our talus cone, right? Again, if it hits 33 degrees, rock's going to hit and tumble to the bottom, right? Once you get a pile of rocks here, then it starts building up, till again it gets back up to that 33 degrees, and it goes down again, right? So remember, things are building up as the mountains themselves are coming down, right? Denudation, lowering of the landscape through erosion. All right, talus grade. Uniform accumulation of rockfall material is called a talus apron. So there we got our talus. Material tends to collect in a cone-shaped heaps or talus cones. Now, I don't know if any of you have been mountain climbing, but you're going to see this up in the higher portions of the mountain, okay? Up to where we get past the tree line, where you're getting ready to make the final track to the peak or the crest, right? And some of these rocks get big. Me and my kids, we went and did some mountain climbing when we were in Colorado. And I'll tell you, some of these rocks, it's wild just trying to get across them. It's going to take a while. All right. Slow talus flow in glaciers and rock glaciers. Again, these can be called rock glaciers. So anyway, rockfall. Here's our slide. Landslide, instantaneous mass slope collapse with no fluid flow lubrication, right? Remember, rockfall, no water. Here, maybe a little bit, but not much. Boom. Rock avalanches, okay? So anyway, this is where more than one rock's moving. Lost material leaves a land scarred. You can actually see the land being scarred, okay? Damming of valleys and stream, creation of lakes. So this is that material that makes it down and then plugs things up and makes lakes out of it, right? Remember, as long as you got an inlet and an outlet, and that outlet is smaller than the inlet, you make a lake, right? So here we go. Rotation of the sliding material is called a slump. Here's our flow. Wasting initiator enhanced by addition of water. There we go. We got more water in there. There's my earth flow and my mud flow. Water is the primary force. Clay can enhance the motion as well because clay absorbs moisture. Earth flows. Water saturated land is moved downhill. Again, and a lot of times, like I said, this is tied into the different composition of the soil there. Maybe there was a hole or a depression there and it filled in with other stuff. And so it doesn't have the same materials as the surrounding stuff. So whichever, again, water takes the path of least resistance, it's going to rush that out. Now, if that was a big mountain peak that was covered by dirt, you'd see the surrounding area erode away, and that would be the only thing that's left, okay? Mud flow originated in arid basins, muddy downslope flows that accumulate with large rocks. Again, mud flows, you can look up some mud flows. People build big farms and stuff on agriculture areas, okay? The debris flow. What's a debris flow? That's when it's got trees and everything, okay? You got some houses, you got some trees, maybe some animals, maybe some people, I don't know. But anyway, you got a whole bunch. A debris flow is just that. It's got debris in it. Is this zone right here? All right, so I had to back up a little bit there. For some reason, Paige decided to skip on me. Don't know what it did. But anyway, there's my zone of creep. Again, here's my rock wall. It's not looking in a straight line. Like I said, it looks like a drunk guy got out there, decided to do some building overnight, right? So anyway, it's real slow though. It takes years and years and years. I've seen places like up in Dodge City, Kansas, walls that are associated with creep. They're still standing, all right? And I'm not gonna say how old I am, but old enough to have been around for a while, all right? Principal areas of slope, again, here we go. Slope angle, vegetative cover, and moisture supply. What did I tell you earlier? Depends on what it is, how big it is, where it is, all that plays a factor. All right, and then terracets. Terracets we see when we do agriculture, especially on the side of hills and stuff. So a lot of times there'll be some creep associated with those terracets, depending how well they've been prepared and made up. And then there's natural terracets as well, where you get these zones of creep at different angles, okay? Solifluction, soil flowage. Okay, solifluction, again, we've already talked, that was the slowest type associated with colder latitudes. Again, that freeze, thaw, okay? All right. That takes care of this. Now I'm going to try and record it, and if I can get it all done in one session, it doesn't time out on me, that's great. Saves me from doing a part two. Now, for my students that are out there, I am feeling like having that today. So chapter 15 is associated with what? Okay, so there you go. Hey, if you're one of my students and you need the points, write this stuff down. Hopefully you're watching these videos. And from now on, depending on what I feel, how I feel, I'll throw these different things up at different times. So you kind of makes you have to watch the whole video. But hey, you get to see my smiling, happy face, right? All right, peace. Y'all have a good day, and we'll talk to you later.